Hello and welcome back once again. This time we are going to talk about four variables Karnaugh map, that is four variable K map. So as you can see on your screen, we have this beautiful graphic representation about how the K map is arranged for the four variables A and B, C and D. So there are four rows and four columns. This side you have these two variables A, B, which will have four possible combinations arranged as 0, 0, 0, 1, 1, 0, 1, 1. Note that the arrangement is always like this: 0, 0, 0, 1, 1, 1, and 1, 0. On the other side, for the C and D, you have again four possible combination. The organization is 0, 0, 0, 1, 1, 1, and 1, 0. So this is how the arrangement looks like. In the cells, there are total 16 cells in decimals starting from 0 to 15. And now let us have a look at the arrangement. So this cell is decimal 0, this cell is decimal 1, then comes 2, and then comes 3. In the binary representation, you also can observe 0 in decimal is nothing but 0, 0, 0, 0 for the four variables binary combination. For the 1 in decimal, your binary logic would be 0, 0, 0, 1. That is A, B, C, D. Then comes 2 here because the AB, that is 0, 0, and CD 1, 0. That becomes your decimal 2. For decimal 3, you have 0, 0, and 1, 1. So that's how from 0 to 15. Now let us see how the cells are numbered. This is cell 0, 1, 2, 3. Then comes 4, 5, 6, 7. Then you start from here 8, 9, 10, 11, 12, 13, 14, and then 15. So you have to remember, first we saw how the rows and columns are arranged for the four variable schema, and then all cell numbers in the decimal is shown in the blue. For example, if you want to understand why 12 is here, so you can see that 12 in decimal is represented as 1100 in binary. That is how the four variable. So you can also organize a truth table for this. Now, let us have a look at this example. There is a function given f that is equal to, in the parentheses, a, b, c, d. So this is a function of four variables, and that has a value equal to summation, sum of, in the parentheses, 0, 2, 5, 7, 8, 10, 13, 15. So all these are called as mean terms. So when these mean terms are given, you have to identify these cells inside the K-map and mark the number in the appropriate cell. For example, I want to mark 0. In the cell 0, I want to mark the min term. So there is this 0, and that's why I marked 1 here. Then I look for 2. In the cell number 2, I mark 1. Then cell number 5, right here, I marked 1. Cell number 7, I marked 1. Cell number 8, I have marked 1. Cell number 10, I have marked 1. Cell number 13, I marked 1. And cell number 15, I again marked 1. So this is how all the mean terms in the parentheses have been marked in the graphical representation of the K-map. Why we are doing this? Our purpose is to simplify the Boolean function or logic expression, or to simplify the logic. That's why the K-maps are used as a graphical method to simplify the logic. Once we are done with that, we now have to make the grouping of the mean terms. Grouping of the mean terms means grouping of the ones. So I have the option of making the grouping. For example, I see that these are four adjacent ones. So I can make this two and these two. Or I can also make these two and these two. However, as I said before, K-maps, the purpose here is to simplify the Boolean expression to the lowest level possible. Lowest logical expression should be there. So instead of grouping the two ones of instead of having a pair of ones, why not I can look for the group of four because they are adjacent to each other. So I can do that. So that is how our intention should be. So what I'll do here, you see that I will make a grouping here. So this is how the K-map grouping will look like. I marked all four ones here. Next, what I see here, there are individual ones at the four corners of this map. So I have an option whether I let them individually marked and draw the square and make a grouping because they cannot make any grouping with another adjacent ones. So let them isolated and represent what they show. However, in the K-map, there is called as folding technique. So from the middle of this K-map, if I fold it to the upward direction or I fold it to the downward direction, these ones, these ones, these ones, and these ones come over each other. So it's like I fold the map from the middle to the upward. So there is this overlap. There is this overlap. Okay. Similarly, from the middle, right over here, from the middle, right over here, I fold the K-map from right to the left. So from the middle, these ones will overlap with these ones. So this one gets overlapped with this, and this one gets overlapped with this, or vice versa. This one gets overlapped with this if I fold the map right in this direction, and this one gets overlapped with this one if I fold the map from the middle in the direction as shown by the arrow. So with that, I should have only one term, the simplified one term. But for now, what I shall do is I will mark the individual ones like this. So that's how it is. That's how it is like this. And we'll see how the simplified term is obtained. So this is how four ones are mapped or the group because they are in the corners. They don't have any adjacent ones. So once that is done, the job here is to write the simplified Boolean logic term for the one. So firstly, we will write the term for the middle four ones that have been grouped. So here we see that there is A and B, which have two values 0, 1 and 1, 1. So 1 is common here. That is the term B is common. And then A is available in the complementary and the non-complementary form. So you can see that A is 0 here, A is 1 here, but B is both 1. So we'll take only the common term and write it accordingly. So here, the first term is B, okay, coming from this one. Next, we see in this direction, right over here, because this is how the mapping is done. So here we see that C and D. So C is available in its complementary and non-complementary form, and D is common. So since C is 0 and 1 both, it gets cancelled. What is remained is D. So the term that we get here is B and D. So that is the first term. That is the first term we get. Now, what we can see from the isolated one, we can write the all terms obtained by these ones here. Okay. So what I need to do is first look at this one. So that is nothing but A bar, B bar, C bar, D bar. That is how the first term is giving me. Look at this, AB00, CD00. So A bar and B bar and C bar and D bar. Okay. Then next term is I look for this one. So this is nothing but 0010. So what I shall write here, or sum of products. I am writing sum of these products. So this is the first product term. This is the product term I obtained from the middle four grouping of the ones. Now, for this one right over here, I see A bar, B bar, C, and D bar. This is how I get the second term. Okay. Now I look for the third one right over here, where I see I can write or A, B bar, C bar, D bar. Finally, that's the one I look for, which is nothing but this one. So I want to write the term for it is A, B bar, C, and D bar. So you see now I've got the four terms, which are product terms, and I got this one. So final expression would be this term also gets added to these four terms, and that's how. But now purpose here is to see whether we can simplify this single logic to a lowest possible logic expression. So for that, we need to observe that here it is A bar, B bar, C bar, D bar. Here it is A bar, B bar, C, D bar. So here, if you see at these two terms, you got C bar and C. So that gets cancelled, and the common that you get out of it is A bar, B bar, D bar. Similarly, here you have A, B bar, then C bar and C here, that gets cancelled. So here also you get two terms. So why not, let me simplify this one. So for this, you can say that you write A bar, B bar, C bar, not C bar actually. This would be D bar actually. This would be D bar. Okay, because C and C bar gets cancelled. Or here, from here, you have common. Take the common terms out. A common, then you have B bar common, C and C bar gets cancelled, and you have D bar common. So now you actually again can simplify. This is equal to, and then again you can simplify here. A bar and A gets cancelled, but what you get is B bar and D bar. So final expression that you want to write here, F is equal to, this is your first term and this is your second term. So that's your term, B, D, or B bar, D bar. So this is nothing but XNOR logic, if you clearly and carefully observe this. So this is how you got the simplification of this logic into this one. This is the final expression that you can have from this one. Okay, so hope you found this model useful and understood how we can actually use schemap to simplify the four variable function, and that is how it looks like. So if you like this model, share it with others. Stay tuned for wider reach. Until then, wish you happy learning.